Imagine turning a tap and nothing comes out. For most of human history, that was reality. Yet ancient civilizations thrived, even in deserts. How? The answer lies in forgotten engineering that still shapes our world today. The first great water engineers were the Persians. Around 1000 BCE, they developed the Qanat, an underground canal that could carry water for miles without evaporation. These tunnels sloped gently from an aquifer to the surface. The Romans perfected this idea on a grand scale. Their aqueducts stretched over 500 miles, supplying Rome with 300 million gallons of water daily. The Pont du Gard in France still stands as a testament to their precision, a three-tiered bridge carrying water across a river. These ancient systems didn't just deliver water, they shaped cities, agriculture, and public health. The principles of gravity-fed aqueducts and underground canals still inspire modern water infrastructure. Next time you turn on a tap, remember the engineers who made it possible thousands of aqueducts that stretched for miles. The Romans perfected this art. Their aqueducts used gravity to move water across valleys and mountains, channeling it into cities for public baths, fountains, but not all water systems were above ground. The Qanats of ancient Persia were underground channels that tapped into groundwater and carried it for miles without evaporation. Engineers dug vertical shafts every few hundred feet to access and maintain the channel. In the Americas, the Aztecs built an ingenious system on an island. Their capital, Tenochtitlan, was surrounded by water, so they constructed chinempas, artificial islands for farming, and a network of canals for transport and fresh water. Medieval European cities relied on wells and public fountains, but also on elaborate systems of lead pipes. Unfortunately, lead poisoning was a hidden cost. It wasn't until the 19th century that scientists connected lead pipes to health problems. Canals, but the goal was universal. Geography and climate dictated the methods. In rainy regions, simple catchment sufficed. In arid zones, survival depended on innovation. The simplest solution was digging down. Wells date back to the Neolithic period, around 8000 BCE. Early wells were simple pits dug into the water table. One of the oldest known wells, found in Cyprus, dates to around 9000 BCE. It was only a few feet deep, but it provided a reliable source of fresh water in a dry landscape. The technology spread and improved. By the Bronze Age, wells were lined with stone or wood to prevent collapse. In ancient China, wells reached depths of over 50 feet. The Chinese also developed the first known well drilling techniques, using bamboo poles and iron bits to tap into deep. In the Indus Valley, cities like Mohenjo-Daro had over 700 wells, each serving multiple households. These brick-lined wells were engineering marvels, some still functional after 4,000 years. They show that organized water management was key to urban life. Back to the Neolithic period. The oldest known well in Cyprus is over 10,000 years old. But wells had limits: depth, water table, and contamination. Springs were prized. They offered clean, flowing water. Many ancient cities were built around natural springs. The Greeks and Romans engineered elaborate aqueducts to channel spring water over long distances. The water flowed by gravity alone, but aqueducts were expensive and required constant maintenance. Most people relied on local wells, rivers, or rainwater cisterns. In dry regions, every drop of water has always shaped where we live and how we thrive. From the first wells to modern plumbing, the quest for clean water is a story of human ingenuity. Early cities like Jerusalem were built around springs. But as populations grew, wells and springs alone couldn't keep up. The Romans perfected the aqueduct, but they didn't invent it. Earlier civilizations like the Minoans on Crete built elaborate stone channels to bring water to their palaces. The Assyrians carved tunnels through solid rock, but it was the Romans who turned water transport into a science. The Romans built aqueducts using gravity, with a precise slope of about 1 foot per mile. They used arches to cross valleys and lead pipes to distribute water. The Aqua Claudia, completed in 52 AD, carried water from 40 miles away. At its peak, Rome had 11 aqueducts supplying over 300 million gallons of water daily. This allowed public baths, fountains, and even private homes to have running water, a luxury that wouldn't return for over 1,000 years. Assyrians and Minoans built channels to carry water over distances. Rome's genius was scale and precision. Using gravity alone, they moved millions of gallons daily across valleys and hills. The Pont du Gard in southern France is a surviving masterpiece, a three-tiered aqueduct bridge that once supplied the city of Nimes with water from a spring. The aqueducts relied on a precise gradient, typically dropping only about 1 meter per kilometer. Roman engineers surveyed the land with a tool called aqueducts, a long wooden level that ensured the channel maintained a steady downhill slope. Any mistake could cause the water to stagnate or flow too fast and damage. Water flowed through a covered channel lined with waterproof plaster called opus signinum. This mixture of lime and crushed pottery prevented leaks and kept the water clean. Along the route, settling tanks removed debris and covered sections protected the water from sun and pollution. When the aqueduct reached the city, water flowed into a massive central tank called a castellum aquae. From there, lead or clay pipes distributed it to public fountains, baths, and a few wealthy homes. Rome's water system was not just engineering, it was a statement of power. Gard in France is a stunning example, a three-tiered bridge carrying water 50 kilometers. The system relied on a precise gradient of about 1/200, just enough to keep water flowing without eroding the channel. The gradient was so subtle that over the entire 50-kilometer length, the drop was only about 17 meters. Builders used surveying tools like the aqueducts to maintain this slope across valleys and hills. Water flowed in a covered channel on top of the bridge, protected from debris and evaporation. At the city end, a distribution tank called a castellum divided the water into lead pipes for public fountains, baths, and wealthy homes. The system delivered over 20,000 cubic meters of water per day to the city of Nimes. This engineering marvel operated for centuries, a testament to Roman precision and ambition. Channel, in the arid Middle East and North Africa, a different solution emerged: the Qanat. These underground channels tapped groundwater in hills and carried it via gravity to lower settlements. Qanats could extend for miles, with vertical shafts every 20 to 30 meters for maintenance and air circulation. The Qanat was a remarkable feat of engineering. Workers dug from the bottom up, using simple tools like picks and baskets. They aligned the tunnel by sighting candles at the shaft openings. The system required precise gradient calculations to keep water flowing without eroding the channel. Qanats provided water for drinking, irrigation, and even cooling. In hot climates, the water remained cool as it traveled underground. Some Qanats in Iran are over 2,000 years old and still in use today, a testament to their durability. And the Qanat system spread across the ancient world, from Persia to China, and later to the Americas. It allowed civilizations to thrive in some of the driest regions on Earth. The knowledge of Qanat construction was passed down through generations, a hidden legacy of sustainable kilometers long with vertical shafts for maintenance. They minimized evaporation, a critical advantage. Meanwhile, the Nabataeans of Petra carved massive cisterns into rock, capturing every drop of rare rainfall. Their system could store enough water to sustain the city through long droughts. In the Andes, the Inca built stone-lined canals and terraces that channeled meltwater from glaciers to their crops. These systems were so well engineered that many still functioned. The Romans, however, took water engineering to an industrial scale. They built aqueducts that stretched hundreds of miles, using gravity alone to move millions of gallons of water daily. The Aqua Claudia, one of their greatest, supplied Rome with over 100 million gallons per day. These aqueducts were marvels of precision. They maintained a consistent gradient of about 0.5% over long distances, just enough to keep water flowing without eroding the channels. Roman engineers used simple tools like the aqueducts to store enough water for 20,000 people through months of drought. Bringing water to cities was only half the battle. Distribution required pipes, taps, and fountains. Romans used lead and clay, the lead pipes being a major health hazard we now know. But at the time, they were prized for their flexibility and durability. The system worked so well that Rome had more public fountains than any city before the modern era. By the 4th century AD, Rome had 11 major aqueducts supplying over 1 billion liters of water daily. That's about the same as a modern city of 1 million people. The system was a marvel of engineering and organization. But the Roman aqueducts were not just about water. They were symbols of power and civilization. When the empire fell, the aqueducts fell into disrepair, and the knowledge of how to build them was lost. Public fountains as the main access point for most citizens. Wealthy homes had private connections, but they also built sewers. The Cloaca Maxima in Rome drained marshes and carried waste away. This prevented diseases like typhoid and cholera from spreading through contaminated water. The Roman system was a marvel, but it wasn't perfect. Lead pipes used for plumbing may have caused lead poisoning among the elite. Some historians argue this contributed to the decline of the Roman Empire, though the evidence is debated. After the fall of Rome, many of these engineering achievements were lost or forgotten. During the Middle Ages, water management in Europe regressed. People returned to drawing water from rivers and wells, often contaminated by waste. Cities became breeding grounds for disease. The Great Plague of the 14th century killed millions, partly due to poor sanitation. It wasn't until the 19th century that major cities began to rebuild proper water and sewer systems. The Industrial Revolution brought new technologies: cast iron pipes, steam pumps, and filtration systems. London's Great Stink of 1858 finally forced Parliament to act, leading to the construction of a modern sewer network designed by Joseph Bazalgette. This system dramatically reduced cholera outbreaks and became a model for cities worldwide. Disease and made dense urban living possible. Water wasn't just for drinking. It powered mills, filled baths, and irrigated gardens. Ancient systems were sustainable by necessity. They used local materials, gravity, and careful planning to move water without pumps or fuel. The Romans built aqueducts that stretched for miles, using gravity to bring fresh water from distant springs into the heart of their cities. At its peak, Rome had 11 aqueducts supplying over 1 billion liters of water daily. These systems required constant maintenance. Teams of workers inspected tunnels, cleared debris, and repaired leaks. The water was distributed through lead pipes, which unfortunately caused lead poisoning over time. After the fall of Rome, many aqueducts fell into disrepair. But the idea never died. Medieval monks and engineers revived water management, building new channels and adapting ancient techniques for their own time. Some modern cities are rediscovering Qanats and rainwater harvesting. The past holds practical wisdom. Work with the landscape, not against it. And perhaps the most important lesson is that ancient solutions are not relics. They are blueprints. By blending old and new, we can build a water-secure future. Important lesson is that water is a shared resource. Ancient laws often regulated access to ensure fairness. We could learn from that. From wells to aqueducts, ancient people solved the water problem, clever engineering and community cooperation. The Romans, for instance, built massive aqueducts that carried water over miles using only gravity. These structures were public works, funded by taxes and built by slaves and engineers. They supplied fountains, baths, and homes, but the system wasn't perfect. Lead pipes caused poisoning, and the rich got more water than the poor. Still, their approach to water as a public good set a precedent. The ancient Romans built aqueducts that stretched for hundreds of miles, using gravity alone to move water across valleys and mountains. Their structures still stand, a testament to their skill. Inside the city, water flowed into public fountains, baths, and wealthy homes. The system was so efficient that some fountains ran continuously, wasting water to prevent pipes from bursting. After the fall of Rome, many of these systems fell into disrepair. For centuries, people returned to drawing water from wells and rivers, and sanitation suffered as a result. Next time you turn on a tap, remember, it took thousands of years of ingenuity to make that simple act possible.